I was telling I will tell you a little bit about what we've done to try and address some of the issues that are related to the task of obtaining reliable and precise stellar ages for all stellar populations around us, especially in external galaxies. And this is indeed a very important task. Obtaining good and reliable ages for external galaxies, and in particular star formation histories, is something that let us have a better peer and a deeper understanding of many of the processes which are related to galaxy formation and evolution. And it's a tool that let us gain more insight in things like, especially when it's paired with other traces like kinematical measurements and elemental abundances, we can start having tools to assess the effects of, for example, interaction with the environment, or the properties and the assembly of cosmological structures. We can look into the interaction between the stellar populations and the gas phase through, for example, feedback or chemical enrichment. And provided that we reach old enough look-back times, then we can also start peering into some processes that happened at the very infancy of the universe, such as, for instance, the epoch of reionization. Now, if we really want to go back to the oldest possible ages, then the best place where we can do this is in galaxies when we resolve the individual stars. And we do that by extracting information from the color magnitude diagram. I show an example here. And this is the main tool I will be using in this talk. And by careful modeling of this diagram, we can then extract detailed star formation histories. For the record, in this talk, when I say the word star formation history, I will not only be talking about the star formation rate as a function of age, but also as a function of metallicity, so the entire two-dimensional distribution of star formation. And you can see an example here in this plot. So ideally, if we want to make a bucket list of what would we like as a data set to try and address some of these problems I mentioned about galaxy formation, we would like to have certain characteristics. And there are a few things that come to mind. The first one is that we would like to have enough measurements over a cosmologically representative sample of galaxies. So this means having a large number of galaxies, for sure, to have reliable statistics, but at the same time also having a diverse sample. So being able to probe a range of different stellar masses and halo masses, many different galaxy morphologies, gas contents, but as well also different environments. So ideally trying to see what's the difference between field and groups and clusters. And on top of that, we would also like to have ages which are as detailed and precise as possible, and if possible, back to the Hubble time and the very beginning, so that we can have precise timing and being able to assess some of the processes that happen on short timescales. So historically, the best way we know to obtain such measurements, the golden path, if you want, is where we are able to build a complete color magnitude diagram. Then we will go and try and extract information from, specifically from this particular evolutionary phase, which is highlighted here, which is the main sequence turnoff. And this makes a lot of sense. We have good reasons for doing so. The main sequence turnoff is the stellar clock per excellence, as we were taught. It's a phase that we understand pretty well. The models are reliable, and they are in reasonable agreement with each other. And indeed, especially for young stellar populations, the main sequence turnoff is indeed the ideal tracer to reconstruct the star formation history. And this is the path we've been going on for at least the past 20 or 30 years, and we had great results. So we used this approach, and we over the years built a complete sample of star formation histories for pretty much all the local group galaxies, and we have revealed some of the complexities that this galaxy present. So we started realizing that there is a lot of variation in the star formation history of galaxies, dwarf galaxies around us, with a lot of the dependence on the stellar mass, but also the host, the infall time, And more recently, this is also the technique which has been applied to increasingly fainter galaxies, pushing into the ultra-faint dwarf regime. And that has revealed a connection between the properties of these galaxies and the formation and quenching of these galaxies and cosmic ray ionization. So this has been an approach which has been extremely fruitful and has given us a lot of insight into the formation evolution of the local group. But it is not to say that this is without limitations. So there are a couple of hindrances in using the main sequence turnoff. And the first one is, you probably noticed that this is a very faint stellar evolution phase. And what this means is that we are limited in the distance in which we can detect such stars. And I show this in this diagram, which is giving you the cumulative distribution of known galaxies as a function of distance from the Milky Way, which is the black line. And the horizontal lines here are showing rough detection limits for old main sequence turn-off stars observed with the Hubble Space Telescope, and in the future as they will be observed by JWST and by 30-meter class observatories. So you can see that, as I was telling before, we are nowadays mostly limited by local group galaxies. So we have a rough detection limit that sits at around 1 megaparsec. And this comprises a sample of around 70 galaxies or so. But even in the future, the situation is not going to improve dramatically. And the reason for this is the enhanced capabilities of the new generations observatories will be hindered by a dearth of galaxies in vicinity of the local group within the 2 and 3 megaparsec region. And so this means that for the foreseeable future, the sample of galaxies for which we will have access to the complete Hubble time star formation history will be limited to a sample which is relatively small, less than 100 galaxies, and also biased with respect to the local group. And that starts raising other questions of whether the local group is a representative environment to study the broader framework of galaxy formation and evolution. There is evidence, for example, that the Milky Way in itself has some characteristics which are unusual for an L-star galaxy. The second issue that comes with studies of the main sequence turn-off is that these stars, especially at old ages, tend to have a very slow evolution, which means that stellar populations that are separated by even a reasonably large amount of time, like a few gigayears, they do not differ too much in the magnitude and morphology of their horizontal branch, and of their main sequence turn-off. And what that means is that we are practically limited into the precision of the ages we can obtain. And this is in the star formation history world. This is typically this precision is typically summarized with this metric called age resolution of the star formation history, which is basically telling you what is the smaller time scale that we can probe. You can see an example here of what's the effect of increasing the age resolution or degrading the age resolution of your star formation history. And you see that even if you have a very rich and diverse formation history, the moment you start hitting resolutions of a giga-year or so, you would really lose most of the details, and you can only probe the average behavior over long time scales. And this means that you can potentially miss on a lot of processes that happens on a few 100 million years or so. This number, the age resolution, is not a fixed quantity. It depends on a number of things. Firstly, it depends on the stellar population age, as I said. And as a rule of thumb, the older the stellar population, the less precise the ages we can derive for the stars. It also depends on the photometric filters that we use to build the color magnitude diagram. And finally, it also depends on the photometric precision with which we observe stars on the main sequence turn-off. And you can see in this bottom left diagram that if we really want to push on precisions which are less than a giga-year or so, you really need to have exquisite photometry of these stars on the main sequence turn-off, meaning that not only we have to to observe these main sequence turn-off stars, if we really want to see the details of the early evolution, we need to have incredibly high signal-to-noise photometry, meaning that we are effectively, even with HST, we are effectively limited to the virial radius of the Milky Way. So the questions that I've been trying to answer is what can be done about these issues? Is there a way to circumvent this and find alternative approaches, or at least complementary approaches to what we've been doing so far? So if we come back to this color magnitude diagram, you can certainly notice that there is a plethora of other stars here populating this plot. And the one I would like to draw your attention on are these on this stellar feature here, elongated, which is called the horizontal branch. And so this is potentially, this is a stellar phase that has a few very interesting characteristics. The first one being that it's bright. It's much brighter, probably 4 or 5 magnitudes brighter than the main sequence turn-off, which means that can potentially be observed at higher distances. Also, it is not as compact as the main sequence turn-off, but it typically spans a large range of effective temperature, and as you will see later, it does have a dependence on the star formation history of the stellar population, meaning that there is information here that can be extracted, that can be potentially used to gain an insight on the age of these stars. Alas, this is a feature which is often overlooked, or at least not modeled into a very high detail in typical star formation history studies. And the reason for it is that this is a complicated stellar phase. So this is just a slide to summarize in a nutshell what are the different properties of the stellar populations that influence the shape of the horizontal branch. And so I will show this by having a reference model here in blue, and the other colors tell you what happens to the horizontal branch if we change one of the different parameters of the stellar population. So first, these stars, the properties of these stars do have a dependence on the age and on the metallicity of the stellar population. And this is, if you consider the entire distribution of age metallicity, this is not other than the star formation history. But there are also other things that have an effect. For example, there is an effect of stellar evolution in that before becoming horizontal branch stars, these stars live on the red giant branch. And during the red giant branch evolution, they will lose a certain amount of mass. And we're not entirely sure how much mass they lose. This is still an uncertain number, but that will have an effect on the shape of the horizontal branch. And in particular, it will mimic age. On top of this, there is also the effect of the helium abundance of the stellar mixture, which also has a strong effect on the properties of the horizontal branch. And generally speaking, the higher the helium content, the bluer the horizontal branch models will be. So you can see there is a number of parameters and a number of degeneracies that dictate the properties of these stars. And this is what over the years gave rise to what is known as the second parameter problem, which is a term that we use to describe the difficulties that we had to gain an empirical characterization and an empirical understanding of what is driving the shape of the horizontal branch. So the case I will make here is that most of the difficulty in dealing with the second parameter problem are not intrinsic to horizontal branch itself, but are mostly related to the environment where we've been studying stellar evolution so far, or mostly, which is globular clusters. And in fact, over the years, we know now for about 20 years or more, the globular clusters are not so simple as we envisioned them originally, but they do host a plethora of substellar populations that have a very peculiar chemical abundance pattern, and this is exemplified, for example, in the abundance of the light elements like sodium and oxygen, and you can see an example on the left. But these chemical abundances appear to be related as well to an overabundance of helium. And as I said, helium is one of the main driver of the horizontal branch evolution. So we do have evidence now that these chemical abundance patterns are one of the main drivers of the unpredictability of horizontal branches in globular clusters. So we see them indirectly from stellar models. We see here on the left, you will see spectroscopy of horizontal branch stars showing that there is this variation of chemistry along the horizontal branch. So one might ask, what if we look somewhere else? Is there another environment where we can have a look at these stars and perhaps not stumble into the same difficulties? What, for example, about dwarf galaxies around the Milky Way? What about dwarf spheroidals? So there is evidence mounting that in dwarf spheroidal galaxies, at least in the field of these galaxies, stars do not have these peculiar abundances that characterize horizontal globular clusters, but indeed they seem to be much more akin to stars in the Milky Way halo. So here you see a couple of plots where these dwarf galaxy stars have been studied in regard of their light element abundances, and they indeed appear to be, you see on the top panel, they are superimposed to a sample of stars from the Milky Way field, and on the bottom you see the stars from globular clusters. So ideally, if that's the case, and we can make the assumption that helium in this system is much more behaved than in globular clusters, and perhaps we can trust the abundances that we get from stellar yields and stellar evolution, it means that then we are only left with two main parameters, and the horizontal branch morphology is only dictated by the star formation history and the mass loss on the red giant branch. So how can we proceed now? How can we break this degeneracy? The way we went about it was to combine information from the main sequence turn-off and the horizontal branch. Indeed, there are galaxies for which we do have access to the main sequence turn-off. So in principle, by having an holistic and synchronized look at the two stellar features together, we could break this degeneracy and try to tell the two parameters apart. And we went about this route by creating a new analysis tool that is based on well-tested routines to model the color magnitude diagram, so the one that has been used so far to model the main sequence turn-off. But that has been also extended to treat very flexibly horizontal branch evolution, to incorporate variable red giant branch mass loss, so that the entire color magnitude diagram can be modeled at once. And we did that by leaving the red giant branch as a free parameter, and so we could fit simultaneously the star formation history of the stellar population and the mass loss on the red giant branch. And even in doing so, even in leaving this free parameter, there is still enough information to improve on the star formation history itself. And one of the reasons that we could do that is that the combination of main sequence turn-off and horizontal branch is extremely good at breaking age metallicity degeneracy. So this is an example shown here, that this is a problem that afflicts modeling of the main sequence turn-off. So you see an example. Here you have two stellar models, of stellar populations, that have very different ages and very different metallicities, but by changing the age and the metallicity in the right way, we can mimic the same main sequence turn-off properties, meaning that we are limited somehow on the precision of the ages we can get from this stellar phase alone. And we do need to rely on external information. This can be, for example, spectroscopic abundances, but can also be another tracer that behaves in a different way. So what happens here, if I now overplot a reasonable horizontal branch models for these two populations, you will see that they are indeed very different, and we're now suddenly much more able to tell the two stellar populations apart. And the reason is that on the horizontal branch, age and metallicities are degenerate in a different way, not in the same way as they are on the main sequence turn-off. And in this particular case, they do work together to change the effective temperature of the horizontal branch stars. So by combining the information between these two stellar phases, we can get much more reliable stellar ages. And we did test that. We used we investigated this by using mock stellar data, mock stellar populations for which we knew the age. So we injected simple stellar populations. And this plot is showing you what's the difference in the star formation history that we recover by only modeling the main sequence turn-off and by also adding the horizontal branch. And for all stellar populations, we can roughly double the precision of our age estimate with the same data set. So the first application we decided to use this tool on was to do an investigation of the properties of stellar populations in those spheroidal galaxies and on their complex characteristics. Indeed, these appear to be relatively simple dwarf galaxies, but we know that they are not. We're not so simple. We have been known for the past 20 years at least that there are at least stellar gradients in their stellar population properties. This has been shown via kinematical studies or through their metallicity or through the properties of their horizontal branch and RR-Lyrae pulsators. And the assumptions that is sometimes made is that these gradients are the result of distinct chemodynamical stellar populations in these galaxies. This is often an assumption which is made in the dynamical modeling of these galaxies. But so far, there hasn't really been conclusive evidence that this is indeed the case, or whether this is just a smooth stellar gradient over the entire galaxy body. So we decided to tackle this issue. We analyzed deep HST photometry for the dwarf galaxy Tucana, which was obtained as a part of the LSEED program. This is a very deep and nice color magnitude diagram that covers all the stellar phases. We did apply our tool and recovered back a detailed star formation history, which was much more detailed than could have been possible only through the main sequence turn-off alone. And here in this updated star formation history, you clearly see that there are multiple phases of star formation. You can distinguish at least two. Perhaps there's a hint of a third star formation episode. So this is indeed supports the idea that the properties of these stellar populations stem from independent and subsequent phases of star formation, which were intercepted by quiescent phases. So that also now prompts the question: what is the cause? What is exactly the driver of this behavior? Not only we did find this evidence, by also carefully analyzing our best models, we did come to the conclusion that there is a strong link between the structure on the horizontal branch, and this is something that many dwarf spheroidal have. They have very structured horizontal branches, and the different events of star formation, so that you can clearly see the phases of star formation in this stellar feature, such that in principle you couldn't even need to do the full star formation history analysis. Just by looking at the shape of the horizontal branch, you could have a rough idea of what the star formation in these galaxies looked like. And you can use this information. You can use these different clumps on the horizontal branch to select the stellar populations and trace, for example, their spatial behavior. And now you are enabled to do a range of different investigations to answer questions related, for example, to radar migrations and feedback, stellar feedback models. Or if you want, you can use this to make a much cleaner selection of these populations that is possible on the red giant branch, for example, and have a much more detailed chemodynamical model of this galaxy, for example, to get a handle on the shape of the dark matter profile. And this is something, for example, that's interesting to people that are concerned with the Caspi chord problem. But we did also measure, as I said, the red giant branch mass loss, not only the star formation history. So we can ask, okay, what does that look like? And so the relation we use a parameterized form for the mass loss is shown in this plot. So our measurement is the red curve, and it is showing that there is a strong dependence between the amount of mass that's lost on red giant branch stars and the metallicity of the stellar population. This was already something that was known. There were already indications in the past decade that it was the case, but we came with a much more precise measurement of this quantity. And what's interesting is recently Marcos Island collaborators, they did a very careful and detailed analysis of the horizontal branch in 46 globular clusters, taking into account the effect of multiple stellar populations and of their peculiar chemical abundances, and came up with a completely independent measurement of this quantity, which is shown here as the gray relation. And it is very reassuring to see that there is very good agreement between the two measurements in these two different stellar systems. So this, on one hand, is reassuring us, is suggesting that perhaps the systematics effect in our analysis are at least reasonably behaved, but also prompts another question of whether red giant branch evolution is then universal. If we're seeing such a concordance in such different stellar systems, then it means that this is a law that applies to many stellar populations. And if we manage to answer this question, then all of a sudden we have a new range of opportunities that opens in front of us. Because if we know reliably and precisely enough the mass loss on the red giant branch, it means that we can use the horizontal branch and the horizontal branch alone to infer a star formation history for resolved galaxy. And if we go back now to this plot where I'm showing the detection limit of the main sequence turnoff, I am now going to overplot the detection limits of the same stellar populations with the same instrument, but for horizontal branch stars. And you can see that we can now push to much higher distances. Already with the HST, we can push to well over 2 megaparsecs. We do have already a few examples of this. This is a dwarf galaxy in the Sculptor group at around 2 megaparsec. But it's even more exciting that with the new observatories coming in the next decade, we will gain access suddenly to a much larger number of galaxies, ranging in the hundreds, extending down to 4, 5, or 6 megaparsecs away. And I'm now showing a few interesting objects that lie in this range. So not only we will have many galaxies, but we will gain access to a whole new range of galaxy types that we haven't been able to probe so far. So, for example, Centaurus A, which is the first giant elliptical galaxy around us, and the first AGN host. We have MET2, so we can access the first massive starburst galaxies. We will be able to probe many more large spirals, which are not so common in the local group, hundreds and hundreds of dwarfs and other stellar types. As well, in terms of environments, we will be able to have a much better characterization of environmental dependencies. We will gain access to field galaxies, but also to other stellar groups and analogs of the local group. And with sufficient investment of observing time, in principle, we could also start to skim the outskirts of the Virgo cluster. But we do not need to go to outside the local group to benefit for this understanding. We can even stay inside our local neighborhood or within our Milky Way to gain insights from the modeling of these stars. And this is the next thing we decided to do, is to look at the very core of our galaxy, of the Milky Way bulge, and trying to assess the occurrence of very old star formation there. And the reason we do that is because the bulge is an interesting region of our galaxy. We do know that most of the bulge is probably originating by dynamical instability of the stellar disk, as we see it composed of a long rotating stellar bar. But we do know that if we move to slightly lower metallicities that typical of the bulge, so around -1 or so, there is also another stellar population which is much more spheroidal in nature and pressure supported. And this is an extremely interesting place to study, because we do know, or at least we do predict from cosmological dark matter models, that halos assemble in an inside-out fashion. So the central parts are the first to come together. And so we do expect that the central regions of a galaxy potential to be one of the best places to look for the most ancient stars that form in the galaxy. And this was already supported by a study of the stellar halo of the Milky Way that showed that there is indeed a gradient in the typical characteristic age of stars as a function of radius. So it would be nice to see whether this is a trend that holds to the very central parts of our galaxies. We do have reasons to think that this is the case. We know from chemical evolution models of the bulge that this region appears to have formed on a very rapid timescale of the order of 1 gigayear. And also we do know that some of the oldest globular clusters in the galaxy do reside in the Milky Way bulge. So they do have ages that are around 13 gigayears and metallicities which are similar to this stellar structure, this spheroidal structure I am considering here. Structure that we know being old already because it has a substantial population of RR Lyrae stars. So we decided that this was the type of star we would investigate and trying to understand a little better. If I ask what is the typical age of an RR Lyrae star, the answer I would get is that RR Lyraes are typically older than 10 gigayears. This is our canonical understanding, and it is already a pretty informative figure and has great value in the archaeological interpretation of all the stellar populations. But if you stop to think about it for a moment, saying older than 10 gigayears is effectively covering an age range which is 25% of the age of the universe. So we asked whether we could try and do better and gain better age measurements for these stars. And the reason we think we can do it is summarized in this animation. This is a mock horizontal branch for a stellar population that has a range of metallicities. And the gray region you see here is the instability strip. So this is the narrow range of effective temperatures that horizontal branch stars need to have if they want to become RR Lyrae pulsators. So what happens is if you take this stellar population and you make it age, you will see that the typical metallicity of stars that fall in this region tend to increase with time. So we do expect a relation between the age of a stellar population and the characteristic metallicity of RR Lyraes. Meaning that, in principle, if we only had two ingredients, so an empirical measurement of metallicity for these stars and a set of suitable stellar models, we could recover an age measurement. This is nothing new. This is something that was known already for 30 years at least, but it was difficult to use models to set an absolute age scale. So mostly only comparative analysis could be done between different populations of RR Lyraes. So this is what we tried to do. And the first thing we did was measuring metallicities for RR Lyraes in the bulge. We did that by modeling the calcium triplet of a sample of over 900 RR Lyrae stars in the galactic bulge. They were observed through the BRAVA RR survey. And so we came up with the first empirical spectroscopic metallicity distribution for a large sample of these stars that we also complemented with other indicators coming from the photometric metallicities. So we did embark in a careful analysis to check the role of systematics and the effect of having different metallicity calibrations and metallicity scales. And so what we converge on finally is this, that these stars have certainly a peaked metallicity distribution, and the median metallicity, the peak of this distribution, falls in a range of roughly 0.3 dexis, just below -1, which is that metallicity range that we are most interested in. So the next thing we did was build a series of stellar population models. We did that using the Basti, isochrons, and horizontal branch models. We did explore a range of theoretical ingredients to assess the effect of theoretical uncertainties on our results. So we did create models with a range of ages, a range of metallicity distributions. We did use two theoretical instability strip prescriptions to extract the horizontal branch stars that would become RR Lyrae. And we complemented this with the red giant branch mass loss that we derived from Tucana. So concocting all of this together and selecting the RLR stars and extracting their mean metallicity, we end up with the plot that looks like this. This is the colored lines here are the different stellar models that we built, and this is showing the median metallicity of our models as a function of age. There is a few things you can see here. The first is that behavior I was telling you about, that the older the stellar population, on average, the more metal-rich the RLR it would produce. And the other thing you can note is, in spite of the different assumptions we make in building our models, there appears to be a degree of concordance between them, good enough that we can come up and try and come with an analytical relation for these numbers, so that we can propose a first theoretical relation between the age and the metallicity of our RLR populations. It is to be noted that this is something that applies only to populations of stars, where you can average on the different stellar evolution phases. This does not apply to single RLR stars or small numbers of them. The other thing you can notice is, if you compare the output from these models with the values that we observe in the bulge of the Milky Way, it does indeed appear that these stars are very old. In fact, they are as ancient as population 2 stars can be. So we come up with an age estimate of roughly 13.4 gigayears. And if you convert that to a redshift range, of course, the error bars inflate because of the nonlinear dependence of redshift and age, but it does appear that these stars formed well within the epoch of reionization. So it is tentative to say that this could be among the oldest stars that formed in the Milky Way, or perhaps, given the age, in the building blocks that later coalesced to form the inner parts of the Milky Way. And as a bonus, these models also allow us to derive an RLR formation efficiency that can be used to estimate the mass of this stellar population, of this spheroidal population in the bulge, that appears to be around 1 to 5% of the total mass of the Milky Way. So I will conclude just with an eye to the future, what's waiting for us. We can explore a number of avenues to use now our modeling of the horizontal branch. The first thing we can do is use the synergy of horizontal branch and main sequence turnoff to deliver improved star formation histories for local group galaxies. And this is especially powerful for galaxies which are so far away that we cannot get very high signal-to-noise photometry of their turnoff. And a prime example is the M31 system. So I'm now involved in an observational program that uses around over 240 orbits of HST time to do a complete photometrical survey of the M31 system. You can see a teaser here. These are the color magnitude diagrams we have reduced. So you can see we do reach down to the main sequence turnoff, but you can also see that there is a fantastic variation of horizontal branch morphology. So it will be really interesting to see what they can tell about us about the properties of these galaxies. For example, it would be really interesting to see at the very faint end, we do still observe red horizontal branches, and that's something which will be very interesting to probe. The other thing we can do is to stick a little bit closer and use galaxies around the Milky Way, for example, for which we do have deep, precise main sequence turnoff photometry, and use that to solidify our mass loss calibration, try to understand if there is variation between different galaxies, if there is what's the exact dependence on metallicity, on the age of the stellar population, and on morphology, for example. And if we manage to do that, and we become more and more confident in predicting the amount of mass loss in this system, then it means that we can now go on and explore regions outside the local group. And the first thing we could do is to exploit the data set that already exists from HST photometry for galaxies which are in the 1 to 2 megaparsec region. So a very good candidate would be, for example, the Sculptor group. And in doing so, we would actually start solidifying on this technique and getting more and more confident in the results, so that we will be ready for for the new windows that will be open with GWST and with ELTs, and getting access to a vast fraction of the local volume. So I think I am short on time, so I'll just leave the summary here. But I hope I've convinced that there is real potential in using the horizontal branch as a tracer of a star formation history, especially when we complement it with much more canonical analysis route like those of the main sequence turn-off. And in doing so, we can actually gain insight on the stellar evolution on one side and getting a good measurement of the mass loss in this system, which is something which we've been trying to do for a few decades at least, but also getting a better insight on the star formation history of the galaxies. For example, in doing so, we revealed already that those spheroidals appear to have a complex star formation history that at least alternated in phases. And so we can now start asking the question of what is the prime cause? Is it the environment? Is it like the stellar feedback that is causing these complex star formation histories? But also we were able to peer into the properties of RLR stars and trying to derive a better age estimate for these stars that revealed how the core of the Milky Way really appears to be the host of very ancient star formation, perhaps the first population 2 star formation that happened in these galaxies. And there is also, as I say, this very nice prospect for the future where we can possibly just let go of the main sequence turn-off and use the horizontal branch as a complementary proxy to get star formation histories at greater distance.